First, I told you last time that the character of a group on a benzene ring influences the regioselectivity of the subsequent reactions. So recall that I said that for regioselectivity of a reaction on a benzene ring, for example, this chlorination reaction, if we start with a benzene ring that already has a methyl group on it, all the carbons of the ring are no longer identical. You've got ortho, meta, and para carbons, and that for this methyl group, you tend to see the subsequent reaction happen on the ortho and para carbons, but not on meta. And the same is true for a methoxy group. Both of these share the characteristic of being electron donating groups. And the rationale for this regioselectivity is really actually quite straightforward. It all has to do with the stability of the carbocationic intermediate that you get when you do the reaction. So let's draw real briefly how the carbocation would look if we added the nitro group at the ortho position relative to the methoxy ring, okay? So the nitro group would be here. And remember that when we do electrophilic aromatic substitution reaction, this is the hydrogen that used to be here on that carbon, on the ortho position, and then we'll use maybe pink for the nitro group. The positive charge is on the adjacent atom, okay? And we would, of course, get that by having having pi electrons from the benzene ring attack the nitrogen of the NO2 plus electrophile. So this is the intermediate. And notice that in that intermediate, when we substitute on the ortho carbon, I'm going to number the carbons of the ring now. Let's number relative to the nitrogen, 1, 2, 3, 4, 5, and 6. Do you see that positive charge in that intermediate? What carbons can it be on by resonance? 2, 4, and 6, right? Yellow is hard to see. Let's go orange. 2, 4, and 6. Notice, though, that when we put the nitrogen at this position ortho to the methoxy group, and we know that that methoxy group is a resonance electron donor, notice we have this additional resonance structure available to us. That is, lone pair electrons on the methoxy oxygen can donate into and form a pi bond, thereby stabilizing the positive charge on carbon 2 and delocalizing it out onto the oxygen. That is the impact of a resonance electron donating group. You get an additional position where, sorry, I did that wrong, didn't I? You get an additional position where the positive charge can be because of that electron donating group. That stabilizes the carbocationic intermediate. Let's contrast that with what I'm going to write down as the hypothetical meta carbocation. Let's go ahead and put the nitro group at the meta position relative to the carbocation. That would be like this. Let's see, yep, this one, and then the positive charge would be here. Now again, we'll number relative to the nitro ring, and I want you to tell me which carbons can have the positive charge in this carbocationic intermediate. I'm sorry, are you angry at how I counted there? I'm angry at how I counted there. 4, 5, 6. Okay, that's better. Which ones? Again, 2, 4, and 6 relative to where the nitro group is. But notice that in no case is the positive charge ever adjacent to the methoxy group. So this intermediate does not benefit from the electron donating effect of the methoxy group. So this one, because of the electron donating effect, is more stabilized. That's the origin of ortho-para selectivity for electron donating groups. Putting the new group at the ortho and para carbon relative to the donating group allows you to go through a carbocationic intermediate where the donating group stabilizes the positive charge. That's all there is to it. You can memorize the donating groups are ortho-para directors. It's helpful to know why they are, and this is why. Follow-up questions about that? We're not going to draw today, because we don't have time, the para carbocation, but you could do it and probably should do it and convince yourself that when you put the nitro group at the para position relative to the methoxy group, you go through a carbocationic intermediate that likewise would have positive charge on the carbon adjacent to the oxygen. So that's why donating groups are ortho-para directors. Okay? Now this is true even for, say, weak resonance donating groups. So if we had a bromo on there to begin with, and then wanted to do a subsequent reaction, since we're on the nitro kick, we would likewise, with the bromo donating group, see exclusively ortho and para substitution. For the same reason, if we draw, say, the ortho carbocation here, where here's the nitro group, here's the bromo donating group, it turns out that bromo is not a great donating group relative to, say, methoxy, but it's still got lone pairs, and so when push comes to shove in a carbocationic intermediate, the lone pairs on the bromine can donate in and stabilize that carbocation. So even though the bromine is a weak resonance electron donating group, it will still prefer ortho and para substitution. All of the resonance donors are ortho-para substitution directors. All of the inductive donors like alkyl groups are ortho-para directors. Questions about that? Yeah? So what do we mean? Yeah, so is bromine still considered a deactivating group? There's two influences I've tried to talk about of various groups on benzene rings. You've got regioselectivity, that's what kind of director is it? And then you have activated versus deactivated. I wish your text had said more reactive or more nucleophilic versus less reactive or less nucleophilic. We have groups that are, for the most part, groups that are ortho-para directors will also be more reactive than benzene, whereas groups that are meta-directors will tend to be less reactive than benzene. The one exception to that are the halides. The halides are resonance donors, so they are ortho-para directors, but their electronegativity and the length of the carbon halide bond limits their ability to make the ring electron rich, so they are less reactive than benzene. That's a distinction without a real practical consequence unless you're answering the question, which of these is more reactive than benzene? The halides, you'd say, are less reactive. Okay. Right, so similarly, we can justify why electron withdrawing groups by resonance are meta-directors. Let's just show acylbenzene like this, where you've got a ketone attached to the carbon of the benzene ring. This is a resonance electron withdrawing group, and it's also a meta-director. If you were to do, and we'll stick with the subsequent nitration reaction, if you were to do nitration here, you would put the nitro group exclusively on the meta-carbon. And the reason for that is that is not that the meta position is so much better than the other positions, it's just less bad. And to demonstrate that, we're going to compare the carbocations. So here is the carbocation you would get from, and this is the hypothetical ortho carbocation. So let's put the nitro ortho to the ketone. That puts the positive charge adjacent to the ketone. Let's now do the meta carbocation, where here is the ketone. The nitro group is now at the meta position. This is the carbon that has the, the positive charge. And let's consider first, again, where that positive charge can be. We won't number the carbons because we don't have time to do so, but you can see that on the left, the positive charge can be adjacent to the ketone and at these two other positions, whereas on the right, in the metacarbocation, the positive charge is never adjacent to the ketone. Do you see that distinction? Okay, why should it be bad for the positive charge to be adjacent to the ketone? Any ideas? Go ahead. Right, the carbonyl carbon itself is electron poor. There's a partial positive charge on it. If you want, you could draw a resonance structure for the ketone, which would actually put a positive charge on the carbonyl carbon. Let's see, paste, please. On the carbonyl carbon adjacent to the positive charge in the ring. In other words, the electron withdrawing group makes a bad carbocation worse by putting an electron poor carbon near the carbocation. Okay, all I did to get from the resonance structure on the top to the one on the bottom is move the electrons out onto the oxygen. So this is why ortho and para substitution are bad when you have an electron withdrawing group. Okay? All right, so now we're prepared to practice. And we want to practice not only 2, but maybe 3 groups on a benzene ring. And we also want to practice synthesis and strategy. So we've got a few examples that we can go through. Let's see. Let's go through some of these in the forward direction, and then we'll worry about them in the reverse direction. So we're going to start out with a methoxy group. And let's do a Friedel-Crafts reaction. Let's just install a methyl group via a Friedel-Crafts reaction. So you tell me, what's my product? Where should the methyl group go? Ortho. And in a separate product, para. And you know that because methoxy is a resonance electron with donating group, and therefore it has ortho-para regio selectivity. Okay, this is the ortho product, this is the para product. Which of those is the major product? Trick question, we never said, you get both of them. Okay? If you wanted to do a synthesis and you needed just one of these, is that okay? Yep, totally fine. We're going to assume that since we can't really get a lot of selectivity between ortho versus para, we're going to assume and hope and pray that their properties are sufficiently different that we can separate them easily. That's always the fallback position of the organic chemist. If you can't get a reaction to give you your desired product in 100%, you just hope that you can separate it from all the other undesired products. So in synthesis, that's what we're going to do. However, it would not be correct to draw the meta product as the product of this reaction. Is that clear? Okay. So suppose our desired regioselectivity was this ortho product. Then let's go ahead and do a subsequent reaction. Let's do a chlorination reaction. So let's use Cl2 and FeCl3. Now we have a slightly more challenging situation because we need to consider the various preferences of these two groups attached to the benzene ring. So I'm going to label the methoxy orange, and I'm going to label the methyl group blue. We're going to note that methoxy is an ortho and para director, whereas the methyl group is likewise an ortho and para director. So that's fun. Which carbons is, let's label together the carbons that methoxy is going to prefer. So that should be this one, or this one. Could we put an electrophile at that carbon? Why not? This is a substitution reaction. There has to be a proton to be removed in the next step to restore aromaticity. We sometimes call carbons that are already attached, well, that's a term that we're not going to use, so never mind. So that one's not an option, okay? The one that's already attached to something that's not hydrogen, not an option because we would lose the chance to restore aromaticity. Let's look at the carbons ortho and para to the methyl group here and here. So we can see there's a difference in preference, right? Methoxy would prefer the orange carbons, methyl would prefer the blue carbons. When you're in this kind of conflict, the principle that your text gives you to solve this problem is the strongest activating group wins. Okay, and so this is where a table in your text is going to be useful. It basically ranks the donating groups in order of how good they are at donating. Okay, and in that list you have things like nitrogen as better than OH or methoxy. Right, you've got sort of most activating here. Least activating would be things like nitro. And in the middle would sort of be the halide, sort of deactivating, but still ortho and para directors. Alkyl groups would show up here. You could do any sort of kind of alkyl group, maybe a tert-butyl group. Also down here would be the acyl groups. So you can use that to get an idea of which groups are more activating, more electron donating, and then you just pick the one that donates best. For the activating groups, generally the resonance donors are better than the inductive donors. And then among the resonance donors, it really tracks very well with nucleophilicity and electronegativity. Why is nitrogen a better donor than oxygen? Because nitrogen's less electronegative. Okay? So we would say here that the methoxy group is the strongest activating group. And therefore, in our products, we're going to show only the ortho-para preference of the methoxy group. In other words, we're going to leave the methyl group alone. Sorry, I guess I can spell out methyl if I want to, but oh dang, I got distracted. Okay, so we need a product with its para to the methoxy group. We also need a product that is ortho to the methoxy group. Yes?
Let's say we have two methoxy groups, methoxy
Good question. So what if I had another methoxy group there? They have equal preferences. Would I have products on every single carbon? Yay. You know what? I get to sidestep that question. Do you want to know why? Because the thing that you've just drawn is symmetric anyway. So yeah, I would expect to see substitution here, and it's the same thing on the other side. I'm not going to put you in that situation. It's interesting, but yeah. Go ahead.
So for the example of the chlorines and the methoxy and the methyl groups right next to each other,
Yes.
you couldn't have done that. You can't add something to two meta groups.
Okay. Good. So this product is making some of you uncomfortable. If you're not yet uncomfortable with it, as you continue to study over the weekend, you will become uncomfortable with it. And the reason for that is that you will learn something from the text, which tells you that if, for example, I had, I'm trying to figure out what situation would actually give me this. Okay, fine. We're going to actually come back to how you would make this one in the first place, because it's kind of fun. But if you have two groups that are already meta to each other, and your text tells you you can't put something between two groups that are already meta to each other. The reason for that is sterics. So if we were going to do a subsequent reaction, I have to pick this carefully. Maybe let's just do the sulfonation reaction. You would expect the strongest donating group to have its preferences met. That's the nitro group. We're going to exclude this position. The chloro group also prefers ortho and para, so actually the preferences agree with each other. You would expect to see these two products, but not the others. But not the other one where the new group would be between the NH2 and the chloro, okay? But notably, we don't, and I'll even draw the one. I don't want to draw it, but I will. So we don't see that one. And the reason is because the position that's ortho to two other groups or in between two metagroups is sterically hindered. Now, how does that differ from the situation here? When we get this product, this position here is only ortho to one group. It's clear on the other side. So you should not memorize the rule in the text to mean I can never, ever, ever get this. You have to be more precise. You can get that sort of 1, 2, 3 pattern of substitution if you start with things that are already 1, 2, and you put something on the side. You can't get there by starting with things that are 1, 3, and then going to 2. Does that help? Okay. What else? Yeah. Yep.
So when we're talking about this, you go either ortho or para.
Yes.
If you're going to have a halide group with a para on, better form of organic spot.
Would it be better to have the halide group para versus ortho? No, there's no steric problems at this carbon. I suppose you could argue that the percentage isn't going to be 50-50, and you're right. We haven't really I haven't really taught you how to think about, nor do I actually know in my head really how to think about whether the ortho is better than the para versus vice versa because of sterics. That's probably a decent argument, and you might expect the para to be major, but I'm not going to ask you that.
But also the first step when you're adding the methyl group, you added ortho in that example, so we're going to add the halide down the road and then go the para route for the methyl group would be better. You can add ortho.
I'm sorry, I'm not sure I understand. Are you asking could I do the halide first?
No,
I'm afraid I'm in a situation that my mother summarizes somewhat violently with, "You're cutting, but I'm not bleeding," which means I don't get it. I think the answer, I think if I understand it correctly, you're wondering if there's an innate preference for para-substitution and versus ortho. The answer is not for us, and we're going to assume that you can isolate the ortho from the para product and use whichever one you need for the next step in the synthesis. That may not answer your question. If it doesn't, please come talk to me and try again. Third time might be a charm. All right, what else? Yes?
Can you explain why CH3 is electron donating when there's a panel electron?
Right, how is CH3 electron donating? The way to understand this is probably, let's see, did I do this here? I think I did, yeah. So it's an inductive effect. And the sp2 carbon of the benzene ring to which the CH3 or alkyl group is attached is more electronegative than sp3. It has more S character. sp2 carbons are more electronegative than sp3. So it's purely an electronegativity argument. It donates through a dipole. So not as big as, not as good of an effect as resonance, but still enough to drive that preference. Did I see another hand? Yeah.
How important is knowing the lists of strengths of the withdrawing and donating groups?
How important is knowing this list? As I said, I think you can get there with a few basic principles. Resonance donors are better than inductive donors. That's principle one. Okay, actually, principle one is halides are weird. Halides are ortho-para-directors, but they're not strong activators. Resonance donors are more activating than the alkyl groups. And then if you have to choose between resonance donors, just follow your electronegativity instincts, and you basically got it. Okay, yeah?
The textbook talked about halogenation of the activated benzene.
Yeah.
So since there's no amine, that's activating it.
Yep.
It says that it will throw a halogen on each of the sides.
Yep. This is your text has a lot of these, and I always struggle with whether to talk about them or not. I've had you read them and be prepared for that particular one. Your text says that the strongly activating rings, the strongly activating groups will mess with halogenation because they will actually do polyhalogenation. I'm sorry, I know it's going to drive somebody crazy that I put me over here and CH3 over there, but get over yourself, it's fine. I'll get over myself too. Okay? Yes, this is observed to happen, and the workaround is to simply lose the Lewis acid catalyst. I'm just repeating what's in your text at this point. So if you just use regular chlorine, then you can get only mono halogenation. That's great. And but in my current magnanimousness, I'm not going to make you worry about that. Okay? Probably you're going to have to track it on the study guide and problem sets, but you're not really going to have to worry about that. Yes?
Kind of a similar question. There's another with the Friedel-Crafts reaction where it reacts with aluminum chloride.
Yeah, so the problem, there's all kinds of actual problems with the Friedel-Crafts reactions that we might want to deal with. One of them is that your text says that anilines, if you got the NH2 lone pair and you try to do a Friedel-Crafts reaction, nothing happens. And the problem here is that the Friedel-Crafts catalyst is a Lewis acid, and the aniline is a pretty strong Lewis base. And remember, for the reaction to happen, the Lewis acid catalyst needs to react with the lone pairs on the chloro, but the lone pairs on the nitrogen are more reactive. And so what ends up happening is the nitrogen from the benzene ring ends up attacking the aluminum of the Lewis acid catalyst, and then here is the sad and lonely alkyl halide who can't do what it needs to do, and the reaction's basically shut down there. So, yeah, that is a problem. I do want you to be aware of that one. The other potential problem with Friedel-Crafts reactions is they don't work well if you have strongly deactivating resonance electron withdrawing groups. So we'll just call those strong resonance electron withdrawing groups. If you try to do either a Friedel-Crafts alkylation or acylation on something like that, nothing happens. NR means no reaction. I guess I should have just put the big ekis there. Okay, or dos ekis. Okay, so that is something that I want you to be aware of. And you'll often have to plan around that as you're thinking about syntheses. I'm trying to think whether it would be useful to do an example before we move on to other questions. So is it related? Go ahead. Yeah, is a carbonyl carbon considered a strongly deactivating, strong resonance electron withdrawing group? Yes. So if I tried to do this, what's the right catalyst there? Aluminum? Also not. So you have to sometimes plan the order. You have to let the types of groups you're putting on and their relationship to each other to help you plan the order in which you're going to put groups on. All right, let's maybe do a couple of them. Let's start with, let's actually make this one. All right, so I want to make this one, and I'm going to make it from just benzene. Okay? So let's talk strategy. The important thing to realize here is that these two groups are meta to each other. Now that's a problem because if I just go and start with putting on the chloro group, anything after that, the chloro is an ortho and para director. So anything I do after the chloro is not going to have meta spacing. If I did the NH2 group first, anything I did after NH2 is also not going to have meta spacing. This is where the derivatization reactions that I introduced are going to help. You remember there's some reactions where we can switch, whether a group is a donating versus a withdrawing group. We can do that with the NH2. We can get the NH2 from something else. Who remembers what that was? That was NO2, right? So you could start with nitration. That's going to make the key carbon-nitrogen bond, and it installs something that is a meta-director. You could then put in the chloro group second. The nitro group is a meta-director, so that enforces the desired regiochemical preference, the desired meta-ness of those two. Then what's the reaction I do to convert nitro to NH2? That's just hydrogen and palladium on carbon. That's a reduction, the nitro reduction reaction. Okay, so that's an example where you sidestep a particular problem, a particular challenge by using that kind of change. All right, let's do some others. Some of these are going to be right out of your text. Any questions on that one? Okay. Good. Yeah, I like that one. Sort of, do I? Yeah. No, we don't need to know the mechanism for this nitro reduction. All right. Okay, I'm just choosing one from your text. This one's 20.61, I think, E, if you want to revisit it at a later time. BR. Okay. So when you see something like this, again, you'll look up the fiery SpongeBobs of doom, and that's what you're inclined to do. As you look at this, you see, okay, I know how to put an acyl group on a benzene ring, and I know how to put a bromo group on a benzene ring. This one would just be Friedel-Crafts acylation. Focus to begin with on the bonds between benzene and something else. Then the BR, I know how to do that. That's just halogenation. I'm a little bit worried about this because that's not a typical R group. Some of you are going to want to invent chemistry. Some of you are going to be like, well, can't I just use this and do a Friedel-Crafts reaction? And the answer is, actually, you might not appreciate this, but anytime you invent chemistry, there are problems that you may not anticipate. You have basically a carbon that's attached to a neutral kicker-offer with a super good leaving group. And so, frankly, that one probably isn't that stable. So that's not a good strategy. You got to think of something else. Okay? So how would you do this? Well, if I don't know how to make this bond directly, you could ask yourself, do I know how to make that one? And the answer is, yeah, I could have made that one. Sorry, I don't know what I'm erasing here. What if I had a good leaving group on that benzylic carbon? That's this one. And then what if I just used this as a nucleophile in sort of an SN2 reaction, right? So that's a retrosynthetic step backwards towards something I know how to make. By all means, for the obvious ones, don't worry about taking steps backward. The Friedel-Crafts acylation and the halogenation are pretty easy. But this third group that's weird, it's helpful to take one retrosynthetic step back, okay? Now again, I ask myself, do I know how to make that one? And the answer is, well, some of you are again going to say, could I do something like that in a Friedel-Crafts reaction? And the answer is, you'd be inventing chemistry. I don't actually know if it works, but there is a better way. And that is that we have learned a derivatization reaction. I can put that bromo there by radical benzylic halogenation. That's one of these reactions we learned that you can follow up a Friedel-Crafts alkylation with. So that's using light, UV light, and bromine, and the starting material is just the corresponding alkyl group. And remember, that works because the benzylic position is really reactive to radicals because you go through an intermediate that's a resonance stabilized benzylic radical. So now as I get there, I've taken two retrosynthetic steps backwards. Now I have something where I know how to make this one, I know how to make that one. Now how do I do that one? Just that's Friedel-Crafts alkylation, right? So now we're getting somewhere. Now we're down to the level of sort of elementary electrophilic aromatic substitution reactions. We're not done yet though, because we got to decide what's the right order to do things, okay? And our key issues here are going to be, first, regioselectivity. So we ought to identify what each of these is. Methyl is an ortho para-director, so is bromo. The acyl group is a meta-director. And second, we're going to have to remember that Friedel-Crafts sucks for rings that, do you guys actually text that or do you write out the CK? Okay, yeah. Thanks. I gotta work on my text vocabulary. For example, this week I learned that IKR is, I know, right? Yeah. What's that? If I knew, I wouldn't be asking you. Sorry. That's a Phil Dunphy bit from a commercial based on Modern Family. It was fantastic. I like to try that one out all the time. I actually knew that was if you know, you know. Okay, sorry. Friedel-Crafts doesn't work for rings that have resonance electron withdrawing groups on them. Okay, so let's think of good strategy. We note that these two are ortho and para to each other. We note that these two are meta to each other. Sometimes you're going to find that the order matters. Sometimes the order doesn't. Sometimes there will be two good pathways to make something and an alternative third pathway that doesn't work. So what do you think? What should we put on first? Actually, what should we not put on first? Okay, we're not sure. I would say priority number one is don't put on the acyl group first, because then you can't put on the methyl group afterwards. Okay? So now let's ask, is it going to matter whether we put the bromo on first or the methyl group on first? Maybe not. If they're ortho to each other, they're going to disagree on their preference for where the third group is. But the methyl group's a stronger activator, so we probably get the right thing. So that one probably doesn't matter. I'm going to just say, for fun, let's try the methyl group first. I want to lead with the methyl group because the addition of the alkyl group is going to make the benzene ring more reactive in a subsequent step, so maybe that's going to make it easier or faster to do the next reaction. Okay, that's easy. What do you want to do after that? There may be a couple of pathways. Let's look at the pathway where we put the bromo on first. And what I'm going to do, you might hate, I'm going to just draw the desired ortho one, and I'm going to say that we would also get the para one in parentheses, but we're going to separate it out, and that's totally fine. Your text does this all the time in a synthesis, and you're free to do so as well. Are you okay with that? You're going to tolerate it. That's fine, I suppose. All right, then the third step would be, let's try Friedel-Crafts acylation. Now the question is, let's look at the two donating groups, methyl versus bromo. Methyl's going to prefer these carbons. Bromo's going to prefer these, and methyl is the most activating one. So probably it's fine when you're in that conflict, probably it's fine to expect that you can get that product. Okay? What about the alternative? What if we did, instead of that, what if we did the Friedel-Crafts acylation first? Presumably that would go on the ortho and the para carbons. The one that we want is the para one, so we'll separate them. I'm going to write over here that we would also get the ortho. Then third reaction is bromination. Again, let's look at the preferences of the groups. Methyl's going to prefer the ortho position. How about the ketone? What's it going to prefer? Meta position. So I actually like this pathway better because it takes us through something where there is no conflict between directing groups. They both reinforce each other. But both of these answers are totally fine. Okay. Now we're not done, because to get where we need to get, you're going to have to go back, and I'm not going to write it, but you're going to have to go back and do the radical benzylic halogenation and then the SN2 reaction to install the ether. Yeah?
When you do that SN2 reaction to install the ether, wouldn't that also kick the bromine off if you already added it?
Yes. No, actually, sorry. So your question is, if I do, at this stage, do the SN2 reaction, is this going to attack this bromine? The answer is no. We don't do SN2 reactions at sp2 carbons, so that one's relatively safe.
Okay.
Yeah.
And so you're saying that whether or not we do CH3 first or BR first, it's fine in this example?
In this example, whether you had done the CH3 first or the BR2 first probably doesn't matter. Similarly, whether you did the BR2 first or the alkyl acylation first doesn't matter. Hint. Well, that got your attention. Hint. It might be useful for you to, just a hint, to review a one-word hint, Wittig. It's not a major part, but you may just want to review what it does and what the starting materials are. You may be called upon to use a Wittig reaction at some point on this exam. Hint, yeah, all right. Let's see. Any other hints? Aromaticity is on the exam. All right, get out of here. Have a good weekend. I will see you Monday.